Okay, welcome back. So we're just having a look at the introductory idea of definite intervals, and we're going to find a number. Now this is done this way, but what I want to do is just go through the same process from 1 to 3 for 2x plus 5. Now we know what 2x plus 5 is, and so it's easy for us to draw a diagram and look at what the area would be from 1 to 3. Okay. So let's do that in our own way. All right. So what we'll have is a linear. Now 2x plus 5 is twice as steep. So if our y equals x goes here, a 2x will be twice as steep, going off like this, coming back down here. Now 1 is about here, and 3 is about here. So what we're looking to do is to compute the area under this trapezoid. Okay, so we can work out a couple of points here, but we don't need to do that. So we'll just use function notation and get the y values. So for 1, using function notation, everywhere there's an x, we'll put a 1. And that will give us a function value of 2 plus 5, which will be equal to 7. So that's a pretty good increment. And then for the second point, using x equals 3, we would see that 2 times 3 plus 5 is 2 3s are 6, plus 5 is 11. So this value over here, that would be 11. So we can clearly see that there's a couple of computations we can make. We can see that that has a width of 2. We can see that the height is from 7 to 11, which is what? 8, 9, 10, 11, 4. So a height of 4. We can also see that there's a rectangle here of height 7 and width 2. So if we add the two areas together, we will get the area under the trapezoid. So if area would be equal to 2 half of 2, half of the base, times the height. This area would be equal to 2 times 7. So we get half the base, that cancels, so we're left with 4. We're going to sum it together with 14. And we get a total area of 14 and 4, which is 18. So we've been able to work out the area under the curve between 1 and 3. That's all of this area here. That's a more traditional way. But so our maths should work. It shouldn't matter whether we use regular geometries. In a sense, we've been explaining that this is how we do this. So what we're going to do is up and under on each of these. So this will become 2x to the power 2 divided by 2. Now they'll will cancel. So we'll just be left with x squared. The 5 has no variable on it, but it will conjure because that's x naught. We've been through that quite a bit. So that will be 5x. Now normally what I would do instead of writing the square brackets, I would just write it like this. And adjacentism is to say by the fundamental theorem of calculus, which is the previous slide. We arrived at that by the fundamental theorem of calculus. This now means that we can put some scaffolding together. And I encourage you to do the scaffolding just as I'm doing it. Whatever x values there are, we'll get a 1. Whatever x values there are, we'll get a 3. So we take this completed value, x squared plus 5x, x squared plus 5x Now, it might seem laborious here, and I actually put the x in. I didn't want to put the x in. I'm not ready for that. Okay, what we're going to do is bomb those brackets with the variables. So one's going in here, one's going in here, one's going in here, and three is going in here. I beg your pardon. And 3 is going in here. Okay, so we've got 3 3s are 9 plus 15. 9 plus 15 is 24. So that's 24. Then we've got the minus sign. Then we've got 1 squared is 1 plus 5 is a total of 6. So 24 minus 6 is indeed 18. Now they're the same, however we looked at it. Okay, that's all we're doing, finding areas and using the techniques. Now you don't have to use the square brackets. Sometimes use the square brackets, or is often used, but you need to read the question and understand what's being asked. Alright, so let's go through a few of them and see if you can do your up and under where it's necessary. Okay, and we can work that out. Now I won't do a geometric interpretation of every one, but you will get that with Wrk1. So if you choose to go and use Wrk1 to check your work, which I encourage you to do, what you'll find is that Wrk1 will give you a geometric interpretation. So in this one here, 0 to 2x4. So let's see if we can integrate a definite integral, and let's see if we can get Wrk1 to validate what we think is happening in that space. And that's all Wrk1 ever is. It's just a validation tool. Okay, so let's just put that there for the moment. And what we can do is we can say, let's integrate. Because I don't know what x4 is. Let's integrate x to the power 4 dx, because we want to say the changes. X, put a colon in, and then we can put our limits of integration. Okay, and that should give us what we want in terms of input. Let's just check it. Okay, so we've got 0 to 2x4 dx, correct? And so then we've got a geometric interpretation. Now, it's not relying on our understanding of this is not a parabola, it's an x4. So in this sense, we've got a sense of the area under the curve, just like we did for the linear one. Okay, so you don't always get an interpretation that way. So what we'll do is we will say that up and under 4 plus 1, just like we did for our indefinites. Okay, and instead of adding plus c here, normally we would write a big plus c, isn't it? Okay, now what we're doing is putting the line 0 to 2, and Jasonism is that we're using this as a result of the fundamental theorem of calculus, part 1. And so part 2 would be, so let me just do that one more time with the actual values, because you can see that I'm not going to be putting all the steps in all the time. Okay. So FTC will be expressed this way now with a couple of big brackets. That's our scaffolding. And we're going to put 0 in whatever x values are in there. And we're going to put 2 in whatever x values there, just like function notation. So we'll set this up as something raised to the power 5, which is x, divided by 5. Something raised to the power 5, repeating that again, because this time it's going to get the 0. And so these are like our A and B points. And so in where we're putting 2, and then we're putting 0. Now if it's a polynomial, we can't do this with trig, sine and cos and such, and e, because they might mean something. Because it's 0, we know that's going to be non-existent. So that's going to end up with 2 to the power 5. Some of you recognise this in the workshop. So that's 32 divided by 5. 32 divided by 5, and we can put units squared because that's the area. Now if we have a quick look at Wrk1, we can see 32 and 5, so we're at least as good as Mathematica. So you'll need to look to the question for it defining what you're going to leave it as a decimal or a fraction. You'll have to check Pearson instructions for that. Alright, so this is a fairly cool thing, isn't it? We're calculating areas under curves, just between limits. How good is that? So sometimes there's brackets that don't need to be there, so I often call them a distractor. So we're going from -2, -1. I saw it and said it before I actually wrote it, taking the brackets away because at this point they're not needed. And so we have x squared minus dx. Now what we need to do is just go ahead and do the integration. So up and under, we'll get x cubed over 3, not doing the +1 by hand, and then minus up and under x squared over 2. X squared over 2. Putting the vertical line, we're going between -1 and 2, and we've managed to establish the limits of integration by the fundamental theorem of calculus. So the next thing then will be to set up our scaffolding, and our scaffolding is our two antiderivatives loaded with values. -1 is going to be dropped into any x values there, and 2 will be dropped into any x values there. So we can set that up as a cube divided by 3 and a square divided by 2, and we will repeat that because this is our a and b for the same function values. Okay, the same function itself. Okay, so minus, and it's laborious, I know, but you must have the discipline to do it. So anything in the brackets gets dropped in, -1, -1, 2, and 2. Okay, so that's a 2. Alright, so then we need to be careful here using our nous and our mathematical intelligence that's been developing. We can see we've got a cube and a positive number, 2 2s, 4 2s are 8. So that's 8 on 3, 2 2s are 4 on 2, that's 2. What about this one? Now we need to be careful. This is a -1 with an odd. A -1 with an odd means that the minus will stay internal here. So I'll come back to that. -1 squared will become a positive, so that's no longer something we need to worry about. It'll be a minus and a positive. So let's just do this together. 2 2s are 4 2s are 8. 8 on 3 for the first part. 2 2s are 4. 4 divided by 2 is simply 2. So that's our first bracket. Our second bracket, then we need to be careful. Okay? It's a cube. -1 cubed is still -1. The 3 wasn't cubed, it was only the x. The -1 is squared, so it now becomes a +1. And that is a half. So we've got adding fractions galore, so we need to continue on with that. Alright, 8 over 3, so we're going to make that 3. So the first bracket will be 8 over 3 minus 2, but we're going to call them times of 1 in disguise. So now they're the same family. What you do to the top, you do to the bottom. So the next one here will be the family of 6. So we've got 2 over 2 times 1/3, 2 3s are 6, and the family of 6, then we got there by doing 1 in disguise dressed up as 3. Okay, so we get 2 3s are 6 on 3, so we get 8 on 3 for the first one, minus 6 on 3. Now, we've got minus 2/6, minus 2/6, minus 3/6. And in fractions, it never goes away, does it? So 8 minus 6 is 2/3. That's that minus there. Now, minus 2 minus 3 is minus 5. Minus 5/6. So this is, we'll double those. So like 2 on 2, which is 1 in disguise. So we'll get 4/6 plus 5/6 is equal to 9/6, which is equal to 1.5, or 3/2 units squared. So the area under the curve for this composite of x squared and x, I don't know what that looks like. You can have a bit of fun exploring, and you can go find out for yourself. Alright, so you can look at Wrk1, and you can just have a look at what x squared minus x would be. X squared minus x. You don't even have to do the whole rigmarole. Okay, you don't have to do the whole int thing. You can just say, well, what does that look like? X squared minus x. I have no idea. Okay, it looks like it's a... So what about if I do that? Plot. Hey, what are you doing? Plot x squared, comma, x, comma, x to the power 2 minus x. Let's see what comes up with that. So we're plotting x squared, we're plotting x, and we're plotting x squared minus x. And so it gives you a sense of what happens when you do a mathematical operation of subtraction. So there's our x squared, there's our x. If we subtract those two, we get the green one. Now, it's not necessary for you to become an artisan in this kind of translation, although that does form part of the HSC. But you can use these mathematical tools to help you establish that. And all we did was an integration between -1 down here and 2 for that. Now, I don't know if I can list. I'm just going to try it. I should really have checked this before, but dx, comma, x between -1 2. I don't think it'll do both in the one thing, and that's all right if it doesn't. I can take the plot away, and there's the integral, giving me an indefinite integral. It hasn't done it at the particular spaces that I want. So what I can do is I can just take this away. So I'll go Control Copy and open a new one, and come back here and get rid of the int, and that'll just give us the graph, and then I can come here and just do the int. So I really encourage you to play around with this, okay, because it will really give you an insight. There's our green curve swooping, and there's our curve being integrated, the area between the curve and the x-axis, the area under the curve. So it's very interesting, 3 on 2, 1.5. So we're at least as good as Mathematica. Alright, so those are geometric fun. So I'll just do this one here, and that will be the last for this week. Alright, so I'm going to do the integral. Now let's see if you can do it. I'm just going to skip some steps here. So up and under. Divide by -1 would leave me -5x. -3 up and under x between 1 and 4 by f t c, which will mean I have a couple of gaps here. A and b values. 1 will go in there, 4 will go in there. So I'll get minus 5 on 4 minus 3 times 4 and minus 5 on 1 minus 3, which will give me 3 fours are 12, minus 5 on 4 minus 12, minus 5 minus 3 is negative 8, plus 8. So I've skipped some steps there for you to recognise that, 5 on 4, minus 12 plus 8 is minus 4. So that's a bit easier to make 4. So we'll put our little 1 in disguise here, 16. So we get minus 5 minus 16 over 4 minus 21 over 4, which is 4 5s are 20. So it's minus 5 and a quarter units. Now, can we have negative units? So the answer is that minus there becomes informational. Okay, we can't have negative areas, that makes no sense. So the negative in integration becomes informational. Please be careful of this. Okay, we saw in a previous one that there was a negative bit. So the sum total of this is a plus, and a plus minus this bit. Now that happens in the first stages of Maths 1. You need to check those. So for here, when we get a negative, we want to have a look at this, please, with Wolfram. So let's bring that back and let's do the integral of 5 x to the minus 2. Put a bracket in minus 2. Minus 3, and we're going between 1 and 4 this time. 1 and 4, and I don't know what that graph looks like. It's an upside down something or other. 5 over x squared minus 3. 4 is predominantly 5 1/4. You see that we did the correct thing, but we don't have a negative area per se. We have a net area under the curve in the negative space, but it's not a negative area. So we need to make sure that we understand that distinction. All right, that's enough for this week. I will catch you next week. Bye for now.